Hello students, welcome to my new lecture on motion in straight line, which is continuation of my previous lecture on the same topic. In the previous lecture, I had introduced motion in straight line. We also learned about position, path length and displacement, as well as average velocity and average speed, instantaneous velocity and instantaneous speed. In continuation of those sections, that is section 3.1, 3.2, 3.3 and 3.4, in this lecture we will study about acceleration, kinematic equations and relative velocity. The basics of acceleration and kinematic equations and relative velocity are explained in detail and notes are also given. Please note down all the important points as the same are important for your academic examination and competitive examinations. So I welcome you once again. Acceleration. Acceleration is defined as rate of change of velocity, that is dv by dt is acceleration. It is a vector quantity. So acceleration is a vector quantity and its direction is same as that of change of velocity. Change of velocity, please underline change of velocity, that is dv by dt. There are three possible ways by which change in velocity may occur. So previously in point number 1 we said change in velocity. There are three possible ways in which the velocity may change. That is when only direction of velocity changes and acceleration particular to velocity, example uniform circular motion. So direction changes and acceleration particular in such a case is perpendicular to velocity, that is a uniform circular motion. When only magnitude of velocity changes, acceleration parallel or anti-parallel to the velocity. So when only magnitude changes and direction remains same, that is falling from top to bottom or bottom to top, only one direction. Direction does not change, magnitude changes. And when both magnitude and direction of velocity changes, acceleration has two components. One perpendicular to velocity and another one parallel or anti-parallel to the velocity, that is projectile motion. This we will study in chapter number 4. So three possible ways in which velocity can change is either direction can change or magnitude can change or both magnitude and direction can change. So in such cases the motion will be either uniform circular motion or a motion under gravity or a projectile motion. The dimensions of acceleration are m to the power of 0, L to the power of 1, t to the power of minus 2 within square brackets, and its unit is meters per second square. Please note meters per second square. Velocity was meters per second, acceleration is meters per second square. In SI unit, it can also be centimeters per second square in CGS system. Types of acceleration. Uniform acceleration. A body is said to be uniform acceleration if magnitude and direction of acceleration remains constant. Please note, magnitude and direction of acceleration remains constant during particle motion. If a particle is moving with a uniform acceleration, This does not necessarily imply that particle is moving in a straight line. That is, a projectile motion also can be a uniform acceleration. Non-uniform acceleration. A body is said to have non-uniform acceleration if magnitude or direction are both changed during motion. Instantaneous acceleration. The rate of change of velocity of an object at particular instant is called instantaneous acceleration. Please note, at particular instant. If the velocity changes, rate of velocity changes at particular instant, that is called instantaneous acceleration. Therefore, vector A can be represented as limit of delta V by delta t as delta t tends to 0. That is equal to dV by dt. These are all vectorial representations. Average acceleration. The ratio of the net change of velocity to the time taken for change is called the average acceleration. So, A bar is average acceleration equals delta V by delta t. It is very important to know the relationship between velocity and time. The velocity dash time graphs are shown in figures and discussed in this slide. The graph is plotted by taking time t, small t or capital T. It can be represented, time t can be represented either by time small letter t or capital letter T along x-axis. Please note x-axis, and velocity of the particle on y-axis. Please see these figures here. The figures on the top row are time and velocity graphs. So here in case A, the particle is at rest and angle theta is equal to 90 degrees, 0 degrees. So it is making an angle 0 with x-axis. V is constant, it is not varying, and therefore acceleration A is 0. Here A is 0, V is constant, and theta, angle theta is 0 degrees. In the figure B, time is on x-axis, velocity is on y-axis as in the previous case, but theta here, the angle theta between path of the motion and the x-axis is 90 degrees. This is at 90 degrees. V is increasing. You see, as we go up, the velocity is increasing. Therefore, A is equal to dV by dt acceleration, that is equal to infinity. And in case C, theta is equal to 45 degrees. This angle is 45 degrees and this path of motion is inclined. You see, it is inclined at an angle 45 degrees. So V is increasing and therefore A is constant. It is moving with a constant acceleration. Distance and displacement. The area covered between the velocity time graph and time axis gives the displacement. And the distance traveled by body for a given interval of time. Hence, the area covered between the velocity time graph and time axis. This is the time axis. If you want to know uh, the displacement, the area covered between velocity time graph and time axis gives the displacement and the distance traveled by the body for a given interval of time. Here it is time is t1. Similarly, in figure D also you can see the area covered, that is a triangle plus a rectangle. The total distance is equal to addition of modulus of different areas. See here, it is the addition of triangular area plus rectangular area. That is given by S is equal to integral of mod V dt. The total displacement is addition of different area considering their sign. Therefore, total displacement is R is equal to integral V dt. Acceleration. Slope of the velocity time graph represents the acceleration of the particle. Here you see it is a velocity in different velocities. Velocity is starting from V naught here and it is decreasing. And the total displacement, total distance is the area addition of triangle plus rectangle. Similarly here it is starting with the negative and it is all direction and acceleration are negative. If theta is greater than 90, this is the theta greater than 90, A is negative, acceleration is negative. In figure G, theta and V are increasing. You see theta and V are increasing and A is positive. Here it is a positive curve. This is also a positive curve. So acceleration is positive here in this because theta and V are increasing. Whereas in figure H, the angle is decreasing. Here you see the angle theta is decreasing and V is also, velocity is also decreasing. Therefore, acceleration is negative. In figure J, there are different slopes. 0 to A is having a different slope, A to B is a different slope, B to C is a different slope, and C to S is a different slope. Therefore, V changes. Slope of the velocity time graph. So, slope every time represents the acceleration of the particle. Kinematic equations for uniformly accelerated motion. Consider a body moving with a uniform acceleration as shown in the velocity time graph. Let V naught and V be the initial and final velocity. Here you see, please see this graph, velocity time graph. Velocity is on the y-axis and time is on the x-axis. Please draw the figure. O is the origin and y-axis is velocity and x-axis is the time. Let V naught at the point A be the initial velocity and V be the velocity at point B. Here it is marked on y-axis, final velocity. So we have initial velocity and final velocity, and the difference between initial and final velocity is V minus V naught represented by BC, and AC represents the time, total time period. Therefore, acceleration A as defined earlier equals slope is equal to del V by del T. That is equal to V minus V naught over T2 minus T1. Suppose this is T2 and we have taken T1, that is equal to V minus V naught divided by T. Here it is shown here. Therefore, V is equal to, so this is A, V is equal to, simplifying, V is equal to V naught plus AT. Let it be equation number 1. The area under the graph gives the displacement. That is, the area under the graph means triangle ABC plus rectangle ACDOA or ACDOA. That is the rectangle. Therefore, area of the triangle we know is half base. Base is T. t and height is v minus v naught, this area of triangle, plus rectangle is this OD is t into this is v naught. So OD t into v naught. So this is equation number 2. Simplifying, we get x is equal to v naught t plus at square. We also have, simplifying this, x is equal to v plus v naught divided by 2 into t. That is, average velocity is equal to v bar t, where v bar is equal to v plus v naught by 2. From equation 1, we know, here simplifying, t is equal to v minus v naught by a. Therefore, equation 4 becomes x is equal to, this is the equation 4, x is equal to v plus v naught by 2 into v minus v naught by a. This is the value of t from this equation. That becomes, multiplying v square minus a plus b into a minus b is a square minus b square. So, v square minus v naught square divided by 2a. Therefore, simplifying, the equation becomes v square is equal to v naught square plus 2a. Motion of body under gravity. Acceleration produced in the body by the force of gravity is called acceleration due to gravity. Repeat, acceleration produced in the body due to the force of gravity is called acceleration due to gravity. It is represented by symbol g. In the absence of air resistance, it is found that all the bodies fall with the same acceleration near the surface of the earth. This motion of body falling towards earth from a small altitude h smaller than r is called free fall. An ideal one-dimensional motion under gravity in which air resistance and the small changes in the acceleration with height are neglected. Equations of motions are given by v is equal to u plus gt, h is equal to ut plus half gt square plus, and v square minus u square is equal to 2gh. Here we use for gravity the symbol g instead of a. These are same as the previously derived equations. For a body thrown vertically up with an initial velocity u, maximum height reached equals h is equal to u square by 2g. Time of ascent. Time is equal to time of descent. That is, if you throw a body vertically up, it takes same time to go up and same time to come down. That is equal to u by g. Therefore, total time of flight is equal to 2. That is, for going up and coming up, it is 2u by g. Therefore, velocity of fall at the point of projection is equal to u. That is the initial velocity. Therefore, velocity attained by a body dropped from height h is equal to v is equal to square root of 2gh. Let us solve some of the problems in kinematic equations. Number 3. A ball is thrown vertically upwards with a velocity of 20 meters per second from the top of a multi-storied building. The height of the point from where the ball is thrown is 25 meters from the ground. Question number A. How high will the ball will rise? And part B. How long will it be before the ball hits the ground? Take G is equal to 10 meters per second square. So this is a problem associated with the kinematic equation. We have to find the height of the ball to which it raises and then the total time taken. So let us solve it. Please see the diagram on the right hand side. It is given that the height of building is 25 meters. So from this point C to A is 25 meters, which is height of the building. Let the ball rise. Because ball is thrown from point A upwards, the ball goes vertically up to the point B and then it comes back to the ground. So after going down, going up, it comes down. So the distance traveled from A to B will be y minus y naught. And the acceleration of fall will be A, because it is going down, it is minus 10 meters per second square. So y is the total height of the ball reached. So let us solve it. For upward motion A to B, V is equal to V naught plus AT, where V is the velocity, V naught is the initial velocity, and A is acceleration, and T is time taken. Therefore, given V is equal to 0, uh, V naught is equal to 20 meters per second and G is equal to minus 10 and T is equal to what? We have to find out T. Therefore, 0 is equal to, in the equation, V0 is equal to 20 minus 10T. That becomes T is equal to 20 divided by 10 is equal to 2 seconds. This is the time in going up from A to B. From B or point of maximum height, the ball falls freely under acceleration due to gravity. The ball is moving in negative direction y. So negative direction y. We use the equation y is equal to y naught plus v naught t plus half gt square. Y naught is the initial distance. Therefore, y is equal to 0 and y naught is equal to 25, because it is y naught is the height of the building is 25, that is equal to 0, and A is equal to minus g, that is equal to minus 10 meters per second. Therefore, y is equal to, substituting 25 plus 20t in this equation, 20t minus half 10 into t square. So that becomes equation 25 plus 20t minus 5t square. So therefore that equation, rearranging, becomes 5t square minus 20t minus 25 equal to 0. Therefore, solving for t, we get t is equal to 5 seconds. Students, you must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. While that train must be traveling faster than you to be able to pass you, it doesn't it does seem slower to you than it would be to someone standing on the ground and watching both the trains. In case both the trains have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. To understand such observations, we now introduce the concept of relative velocity. The velocity with which an object moves with respect to another object is called the relative velocity of that object with respect to another. Position time graphs of the two objects with equal velocities are shown in figure A. They are straight lines parallel to each other. Please see the figure A, where position time graph A and B are moving with equal velocity. This is object A moving in this direction, and exactly parallel to this A, there is another object B moving in the black line direction. So they are straight lines. Both A and B are straight lines parallel to each other. If XA at 0 and XB 0 are positions of the objects A and B respectively at time t equal to 0, their positions XA t and XBT at time t are given by the relation XA of t is equal to XA of 0 plus VA of t. See here, this is the XA at 0. At 0, this is XA, and at 0, this is XB. And at a time t0, there is some other time xt, this will be XA and this will be XB, and the relationship is XA is equal to XA of 0 plus VAA of t. Therefore, XB of t is equal to XB of 0 plus VB of t. These are the XA of 0. This is the starting point and this is the slope VB into t. So t is the x-axis and x is the displacement is on y-axis. Displacement from object A to object B is given by xBA, that is B to A of t is equal to xB into t minus XA of t, that is this minus this, is equal to XBA, that is equal to XB0 minus XA0. This is XB0 minus XA0 plus VB minus VA into t. This is simplifying these two equations, equation 1 and equation 2. Therefore, relative velocity of A with respect to B is given by VA minus VB. If A and B are moving in the same direction with velocities VA and VB, the relative velocity of B with respect to A is VBA is equal to VB minus VA. This is shown in figure B. Please see the figure B, position time graph, that is, this is the position y-axis and time is on x-axis. A and B are moving in positive direction with unequal velocities. Hence, there is an interception at this point. So, if A and B are moving in the same direction, both are moving in the same direction but different velocities, VA and VB, The relative velocity of B with respect to A is Vb minus Va, and this is shown in figure B. If A and B are moving in the opposite direction, please see here the figure C, they are moving in the opposite direction. A is moving from this direction to upwards, and B is moving from this point to downwards. In fact, it is crossing x-axis also. If A and B are moving in opposite direction, then VBA is equal to VB minus VA, that is equal to VB plus VA. This is shown in figure C. Now we will summarize what we have learned in this chapter. An object is said to be in motion if its position changes with time. The position of the object can be specified with reference to a conveniently chosen origin. For motion in straight line, a position to the right of the origin is taken as positive and to the left is taken as negative. Path length is defined as the total length of the path traversed by the object. Displacement is the change in position, that is delta x is equal to x2 minus x1. Path length is greater or equal to magnitude of displacement between the same points. An object is said to be in uniform motion in a straight line if its displacement is equal in equal lengths of time. So displacement should be equal for equal lengths of time. Otherwise, the motion is said to be non-uniform. Average velocity is displacement divided by the time interval. That is V bar, average velocity, is equal to del x by del t. On xt graph, the average velocity over a time interval is the slope line of connecting initial and final position corresponding to that of the interval. So slope of the line is the average velocity. Average speed is the ratio of total path length traversed and the corresponding time interval. Instantaneous velocity, or simply velocity, is defined as the limit of average velocity as time interval delta t becomes small or delta t tends to be 0. Therefore, v is equal to limit of v bar delta t tending to 0, that is limit delta x by delta t tending to 0 equals dx by dt. The velocity at a particular instant is the slope of a tangent drawn on the position time graph of that instant. Number 8. Average acceleration is the change in velocity divided by time interval during which the change occurs. So, a bar average velocity is equal to del v by del t. Instantaneous acceleration is defined as the limit of the average acceleration as the time interval delta t goes to 0. Therefore, a is equal to limit of a bar delta t tending to 0, that is equal to limit of del v by del t into delta t tending to 0, that is equal to dv by dt. The acceleration of an object at a particular time is the slope of velocity time graph at that instant of time. For uniform motion, acceleration is 0 and xt graph is a straight line inclined to the time axis and velocity time graph as a straight line parallel to the time axis. For motion with uniform acceleration, displacement time graph is parabola with Vt graph is a straight line inclined to the time axis. Point number 10. The area under the velocity time curve between times t1 and t2 is equal to the displacement of the object during that time interval. And for objects in uniformly accelerated rectilinear motion, the phi quantities displacement x, time taken t, initial velocity v0 and final velocity v and acceleration a are related by a set of simple equations called kinetic equations. These equations are v is equal to v0 plus at, x is equal to v0 t plus half at square, and v square is equal to v0 square plus 2ax. If the particle starts at x is equal to x naught, then x in the above equation is replaced by x minus x naught. Next worked example. Question number 4. Stopping distance of vehicles. When brakes are applied to a moving vehicle, the distance it travels before stopping is called the stopping distance. It is an important factor for road safety and depends on the initial velocity v0 and the braking capacity or deceleration. Deceleration minus a. Acceleration is plus a, deceleration is minus a. That is caused by applying the brakes. Derive an expression for stopping distance of a vehicle in terms of v0, initial velocity, and acceleration. Let the distance traveled by the vehicle before stopping be ds, d suffix s. Then using equation of motion, we get v square is equal to v0 square plus 2ax. And noting that v equal to 0, we have stopping distance is equal to minus v0 square by 2a. That is, you put v equals 0 in this equation, you get 2ax is equal to minus v0 square, and a will be is equal to v minus v0 square by 2a. Therefore, ds is proportional to v0 square. That is, stopping distance is proportional to initial velocity, square of the initial velocity. Note, stopping distance is an important factor considered in setting up the speed limits, for example, in school zones. Next question. Question number 5. Two parallel rail tracks run north-south. Tracks are north-south, run parallel. Train A moves north with a speed of 54 kilometers per hour and train B moves with a speed of 90 kilometers per hour. What is the velocity of B with respect to A? And what is the velocity of the ground with respect to B? And part C is velocity of a monkey running on the roof of a train A against its motion with a velocity of 18 kilometers per hour with respect to the train A as observed by a man standing on the ground. So please read the problem once again. Two parallel rail tracks run north-south. Train A moves with a speed of 54 kilometers per hour and B moves with a speed of 90 kilometers. We have to find the velocity of B with respect to A and velocity of ground with respect to B. And velocity of a monkey. A monkey is sitting on the roof of train A against its motion with the velocity of 18 kilometers per hour. So monkey is traveling with the velocity of 18 kilometers per hour with respect to train A. So let us solve it. Answer. Let the positive direction of x-axis be south to north. south to north, positive of x-axis, be south to north. Therefore, given VA is equal to VA, velocity of A is 54 kilometers. Therefore, kilometers we have to convert into meters. 54 into 1000 divided by, it is given per hour. So we have to convert it into per second. So hour to minute is 60 and minute to seconds is 60. So 54 into 1000 divided by 60 into 60, that is equal to 15 meters per second. Therefore, VA is equal to 15 meters per second. Velocity of B, which is running with south in the direction of south, is 90 kilometers per hour. It is given. Therefore, that is equal to minus 90 because it is running in the opposite direction. So, minus 90 into 1000 divided by 60 into 60, that is equal to velocity of B is minus 25 meters per second. Therefore, VAB, velocity of A with respect to B is VA minus VB. VA is 15. So we are required to find velocity of B with respect to A. VB minus VA minus 25 minus 15. That is equal to minus 40 milliseconds. Velocity of ground with respect to B. Therefore, VBG is equal to velocity of 0. Velocity of ground is 0 minus VB. That is equal to minus of minus 25. That is 25 meters per second. Because velocity of ground is always 0. Let the velocity of monkey with respect to ground be Vm. Therefore, relative velocity of monkey with respect to A is equal to V suffix ma. Therefore, V of ma is equal to Vm minus Va, that is equal to minus 18 kilometers per second. It is given, that is equal to minus 18 into 1000 divided by 60 into 60. That is hours converted into second. That is equal to minus 5 kilometers per second. Therefore, velocity of monkey is equal to velocity of monkey with respect to train A plus velocity of A. That is equal to minus 5 plus 15. That is equal to 10 kilometers per second. Let us compare the physical quantities summarily. So, physical quantity, path length is, dimensions are L within square brackets and its unit is meter, represented by symbol by letter M. Displacement, that is change in distance, is delta x. It is also represented by its dimensions are capital L within square brackets and its unit is M, and it is x2 minus x1. That is x2 is the final destination and x1 is initial destination. In one dimension, its sign indicates the direction. Velocity, average velocity is v bar and instantaneous velocity is vector v, and dimensions are Lt to the power of minus 1 within square brackets and its unit is velocity is meters per second. In one direction, its sign indicates the direction. In one dimension, its sign indicates the direction. And it is given by instantaneous velocity is given by limit delta x by delta t as delta t tends to 0. That is equal to, removing the limits, it becomes a differential of x to t, that is dx by t dt. Speed, average speed and instantaneous speed are, the dimensions of average speed and instantaneous speeds are Lt to the power of minus 1 within square brackets and its unit is meters per second. Its definition is, average speed is path length, please note, not the distance. path length divided by time interval, that is equal to dx by dt. Acceleration. Average acceleration is represented by a bar. This is bar here, which is not very clearly legible, but it is a bar. So its dimensions are Lt to the power of minus 2, that is meters per second square. So its unit is meters per second. In one dimension, its sign indicates the direction of change of velocity, that is the delta v by delta t. And instantaneous acceleration is defined as limit delta v by delta t as delta t tends to 0, that is equal to dv by dt. With this, we come to the end of discussions on motion in straight line. In the next lecture, we will take up motion in a plane, wherein we will study about scalar and vector algebra, multiplication of vectors by real numbers, addition and subtraction of vectors, graphical method, resolution of vectors, and vector addition using analytical method. Please note that we have not taken numerical examples, exercises, and multiple choice questions connected with chapter number 3. We intend to combine the numerical problems of chapter number 3 and chapter number 4 as well as their respective exercises with MCQs at the end of chapter number 4. So you please continue with theory part of chapter number 4 in my next lecture. Hence, please study whatever we have taught in this previous lecture in detail and be prepared for my next lecture. Thank you.